Okay, we have a proof from Ashley Carter's Thermodynamics in Chapter 4, problem number 2. The equation of state of a certain gas is pressure plus B, which is a constant, times the specific volume is equal to RT. And its specific internal energy is given by U is equal to AT plus BV plus U naught. Find the specific heat capacity with constant volume. Okay, by definition we know the specific heat capacity with constant volume is equal to, or even defined by, the partial of the system's internal energy over the partial of temperature with, of course, the volume held constant. And what this is, we know that for a change in temperature, the system is going to change its internal energy by so much, and that's what this specific heat capacity is talking about to begin with. Well, luckily, we can use this right here. They give us U, so this one's going to be easy. So we have our partial with respect to temperature of this function up here. A T plus BV plus the initial, which is a constant. So all we have to do is differentiate and hold everything constant except for anything that has a T term in. So these are constants, these are going to go away completely. And that leaves us with our specific heat capacity with our volume held constant is equal to the derivative of AT with respect to T is simply A. Okay, that was the easy part. B asks us to find, it says show that specific heat with the pressure held constant minus the specific heat with the volume held constant is equal to the, I'm sorry, that's not the real number system. Taking abstract algebra, I tend to do that a lot right now, is equal to the ideal gas constant R, not the real numbers. Okay, so we just solved for CV, so we know what this one is. We need to solve for CP. What is the specific heat capacity with constant pressure? It's defined as change in enthalpy over the change in temperature with, of course, the pressure held constant. And this is how a change in temperature affects the system's enthalpy. Just like the internal energy, the enthalpy is a state variable, and it doesn't matter the path that you take. It's always going to be the final minus the initial will give you your change. What do we need to know here? We need to know what H is. So let's find out what enthalpy. Enthalpy is going to be equal to the system's internal energy plus the work done on it, PV. This is going to give us, well, we have this defined right up here. They're giving us U, so let's plug that in. That was AT plus BV plus U naught plus PV. And what is PV? PV is equal to, well, let me put it to you this way. P capital V, our regular volume, is equal to nRT. What is our specific volume? Well, that's when you take the volume and you divide by N on both sides. So this turns into our little v, and this gives us RT. So this term right here can be replaced. Now we have A times the temperature times B times the specific volume plus the internal energy of the system. And now we got plus RT. I think you can probably see this one coming together quite nicely now. Now all we have to do, now that we know H, all we need to do is a derivative dH dt. So that is going to be A plus R. So derivative here gives you A. This is a constant. It's a constant. Derivative here gives you R. So we will plug in, this is our CP. So specific heat capacity at constant pressure is equal to this. So we got A plus R minus what was CV? CV was A. Hence, we have shown it equals R is equal to CP minus CV. QED.